Everyone for coming to today's IEEE colloquium. Today it's our great pleasure to welcome Professor Bill Daly to visit us. Bill is currently the Chief Scientist and SVP of Research at NVIDIA. He's also Adjunct Professor at CS and EE. Used to be the Chair of Stanford Computer Science. Bill really needs no introduction. He has won essentially all the awards in the field. Has been pushing innovative, efficient solutions, hardware and software to accelerate many different types of applications, including machine learning, bioinformatics, and logical inference. Bill is a member of the National Academy of Engineering, member of National Fellow of IEEE, Fellow of ACM, Fellow of the American Academy of Arts and Sciences. Even this year has also won many awards, including the Queen Elizabeth Prize for Engineering, the Benjamin Franklin Prize, the Benjamin Franklin Medal. So today we'll be very excited to hear about the recent trends in deep learning hardware. Now the podium is yours.
Okay. Well, thank you. Thanks for inviting me to Berkeley. I always have fun when I come visit. You know, today everybody's lives are being sort of revolutionized by deep learning. I think it's going to change just about every aspect of our life, and hopefully for the better. I think it's kind of what we make of it. And I decided to get an unbiased view. I'd asked ChatGPT what ChatGPT was good for. And this was the reply. You know, how can deep learning enhance the human experience? And you know, healthcare, smart assistance, education, transportation, entertainment, environment, and so on. As a concrete example of this, this is Agente, which is a agentic system that was built in our Toronto AI lab at NVIDIA, which basically acts like a graduate student in quantum chemistry. If you ask it a question like, what is the activation energy of caffeine? I find that when I drink caffeine, it activates me. It basically answers that question by, you see the graph on the right is a bunch of specialized agents that each carry out a certain task with tools. And the tools may involve preparing an input file with the molecule, running a density functional theory simulation on a supercomputer, and then interpreting the results of that, running some additional codes, and eventually coming back with the actual answer. And you know, this was relatively quickly put together, with the agents fine-tuned for their different tasks here, and it sort of acts as maybe a second-year graduate student in its ability to carry out tasks that the research supervisor gives it. and I could go on with lots of examples, but this is not a talk on applications, it's a talk on hardware. So how did we get to this point where we have these great tools that act like power tools for our brain? It makes us many times more productive. When I need to write a piece of code now, I kind of think about what I want the code to do, and I have Cursor or Claude write the code for me. I don't actually write it myself. It's kind of moved me up a level with the management chain. So deep learning really has three main ingredients. The first ingredient is algorithms, which I've kind of illustrated here by the figure from the AlexNet paper on the bottom. Now, most of the algorithms that are used for deep learning, things like deep neural networks, convolutional neural networks, training them with backpropagation and stochastic gradient descent, have been around since the 1980s. When I was a graduate student at Caltech, I took a course on neural networks that John Hopfield gave a number of guest lectures in. And I thought, these are really neat, but gee, we don't have enough computing power to do this. And I sort of classify them away as an interesting curiosity. The next ingredient is data. And large labeled data sets, like COCO and Pascal and ImageNet, came around in the mid-2000s, about 2005. ImageNet was 2009, with enough images labeled to train these networks. But still, there was a missing ingredient. So you can think of this as sort of the fuel in the air of deep learning. The missing ingredient was hardware that was fast enough to train a reasonable-sized model like AlexNet on a reasonable-sized data net like ImageNet, which at the time I think was a little over 1 million images, in a reasonable amount of time, which was 2 weeks. And that was kind of the spark that ignited that air-fuel mixture and really set off the deep learning revolution. And since then, it's been a wild ride. And we actually, as the primary developers of deep learning hardware, feel a great responsibility to continue making the hardware faster every year, because that's gating the performance of deep learning. This is the number of operations it takes in petaflops to train a state-of-the-art model, starting with AlexNet, where it was a few hundred, and now we're into the many tens of billions of petaflops to train a mixture of experts transformer model. And during this period here, the blue line is sort of when we were building image networks. running them on the ImageNet benchmark, progress was going up at about 3 times per year. That is, it took about 3 times as many arithmetic operations each year to train the state-of-the-art model. But then in 2017, some people at Google wrote this paper called Attention is All You Need, and people started building transformer networks, which put us on this 16x a year trajectory. And the increase in demand has been 10 million over the last 10 years in the number of operations it takes to train a state-of-the-art model. So how do we meet this demand? So I'm going to give some history. I'll start with ancient history. And this is a slide from a talk I gave at the Computing Consortium talk in Washington earlier this year about how government-funded research has been essential to building many American industries. And it really sort of lays the groundwork. A lot of people think, gee, GPUs appeared and everything was fine, but GPUs didn't just appear. There was fundamental work on parallel computing and then on stream processing, which laid out most of the fundamentals of GPU computing with kernels and producer-consumer locality. And these were all DARPA-funded research programs. The thing that most directly led to GPU computing was a program I ran at Stanford to build a streaming supercomputer. Out of this came a language called Brook, which evolved into CUDA. And we ported that to the GPUs of the time, which had programmable shaders, but did not have compute shaders yet. And then I went and I consulted at NVIDIA on the NV50 to put the compute shaders into them. One of the graduate students on the project, Ian Buck, who by the way now is the general manager of data center computing at NVIDIA, went to NVIDIA and took Brook and turned it into CUDA in collaboration with a guy named John Nichols. And so a lot of this stuff would never have happened without government-funded academic research. And it served both to develop the fundamental ideas and probably more importantly, to train a bunch of students who then went and took those ideas to industry and made them into real products. I'm going to zoom in on this part of it, so I won't go into that in detail. This shows sort of the increase in GPU performance on AI inference over the last 12 years, and it's 5,000x. And I actually drew it like this as a linear plot because when I was on the faculty at MIT, I consulted for DEC, and they had this rule that if you were to present to an audience that had anybody above the rank of vice president, you weren't allowed to use a log plot because they wouldn't understand it. But looking at this audience, I think I'm safe to go to this one. And what you see is that we've had this steady increase, basically doubling performance basically every year over the last decade. And this is pretty remarkable because very little, everybody thinks, oh yeah, it's Moore's Law, it's just technology. It's not. We've gotten very little of this from technology. The technology nodes are labeled here. 28 nanometers is in black, 16 nanometers is green, 7 nanometers blue, 5 nanometers purple, and then Blackwell, which is red, is in 4 nanometers. and I've actually gone and looked at each of these GPUs and where they're on this chart and asked, where did the performance come from? And what you see is that through Hopper 2.5x through Blackwell, 3x came from process technology. Out of the 5,000x, 3x is from process. Everything else is from better architecture and clever design. The single biggest contributor, 32x, is from number representation. When we started doing deep learning on GPUs in 2012, we just started shipping Kepler GPUs. The first Kepler GPUs went into the Titan machine at Oak Ridge National Laboratories, which at the time was the fastest supercomputer in the world. And that chip was designed not for AI, because we had just started playing with AI 2 years earlier in 2010, which was too late to really affect the design of Kepler. It was designed to do graphics and supercomputing, high-performance scientific computing. And so for graphics, we had FP32. For high-performance computing, we had FP64. And so we were doing AI with FP32, which is gross overkill. And the energy required to do an arithmetic operation is dominated by the multiplies, and the multiply energy goes as the square of the number of bits. If you think about doing multiply in long form, you generate a number of partial products equal to the length of one operand multiplied by the length of the other operand. And so if you double the length of the operands, you quadruple the energy. Commensurately, if you go from 32 bits down to 8 bits, that's not a reduction of 4 in energy, it's a reduction of 16. So a lot of our journey along here, 32x of that 5,000x, is from going from FP32 down to FP4, which is what we're shipping in Blackwell. And I'll go into a little bit more of that later, and how we're able to make the low precision work. The next thing is complex instructions, and I know this comes a little bit as heresy to people at Berkeley where RISC was invented, but it turns out that carrying out an instruction takes a lot of energy. And I'm going to flip to the next slide, and then I'll come back to this one. Even GPUs, which are very efficient in how they do instructions, because they don't do any speculation, they don't do any branch prediction, all the things that make an instruction in a CPU very costly, but also make the CPUs very good at single-threaded code. The cost of carrying out a single instruction without doing any work, just fetching the instruction, decoding it, fetching the operands, normalized to 45 nanometers, is 30 picojoules. In comparison, the energy of doing a floating multiply add, 2 arithmetic operations, is 1.5 picojoules. So you're basically spending 20 times as much energy on overhead as you are doing real work. It's kind of like a corporation. So over various generations of NVIDIA GPUs, we reduced this. Starting with the Pascal generation, we introduced dot product instructions. So now instead of doing 2 arithmetic operations, you do 8. You basically take 4 numbers, multiply them pairwise together, and sum that all up. So now the overhead's only 5x, but still you're doing more energy and overhead than you are in operations. It wasn't until the Volta generation that we introduced matrix multiply instructions. So a single HMMA instruction, half precision matrix multiply accumulate, takes 2 4x4 FP16 matrices, multiplies them together, that's 64 multiply operations, and then sums that into an FP32 matrix. And if you add all the adds up in there, there's also 64 add operations. So it's 128 operations done with a single instruction. And now the overhead is down to 22%. And in the Turing generation, we introduced IMMA, integer matrix multiply accumulate. It does the same thing, but 2 8x8 int 8 matrices, multiplying together and then summing into an FP32 matrix. And now our overhead was 16%. It is now, without going into a lot of detail, 11%. What this means is that our overhead is so small, our efficiency is essentially identical to that as if we built a dedicated accelerator aimed just at deep learning. If you'd hardwired it for the algorithm, you could at most do 11% better. And by the way, you can't, because hardwired accelerators have overhead too. It's not all arithmetic energy. But we get the advantage of having a completely programmable engine, so we can adapt very quickly as algorithms change. So complex instructions are the next big gain, and that's about a 12.5x gain over this period of time. Process has not been completely a bust, but compared to the heydays of the 80s and 90s, when CPUs doubled in performance every couple of years, and it was almost entirely due to process, and you would get sort of 8x per generation in perf per watt for doing the same function unit. It's kind of disappointing that over 28 nanometers to 4 nanometers, basically essentially an entire order of magnitude of scaling, we get 3x. Sparsity, exploiting the fact that most of these matrices are not dense, but have a lot of zeros in them, gives us 2x. I'll explain that a little bit more later. And then on Blackwell, we kind of cheated. Blackwell is actually 2 die. It's 2 reticle limited GPU die on 1 substrate that we call 1 GPU. So that last jump is doubling the die area as well. I should say that at the same time we were doing all of this, an equal gain, at least equal gain, came from people coming up with better models. So for example, even just looking back at those vision models, going from AlexNet and VGGNet, which basically had a fully connected layer. It had a bunch of convolutional layers followed by a number of fully connected layers, and their arithmetic performance was dominated by those fully connected layers. The next year, ImageNet was run by a network called GoogleNet, which eliminated the fully connected layers and increased the efficiency by more than an order of magnitude in terms of the performance you got per arithmetic operation. Let me jump ahead here. So this brings us to our current generation Blackwell, which is an amazing piece of engineering. It's 2 reticle limited die. The connection between them is something we call NVHBI's 10 terabytes per second of bandwidth. Connect these 2 die together at a few femtojoules per bit to transfer it across. It's really a nice piece of circuit design that was done within NV research, so I'm kind of proud of it. It has 8 terabytes per second of HBM bandwidth from these 8 stacks of HBM 3E memories. And it's an enormous amount of computing power in one thing. But as I showed earlier, we needed 10 to the 7th performance increase to train state-of-the-art models over that time. and we got 5,000. So where does that other several thousand come from? And the answer is parallelism. So for both training and inference these days, it is typically not done on a single GPU, but we chop it up into pieces and we exploit parallelism along at least 3 dimensions. The first is, and it's the easy dimension for training, is data parallel. If I have a 100 million image data set I'm going to train on, I can break that up into what are called batches of images. And I can send one batch of image to this plane of GPUs, and the next batch of image to this plane of GPUs, and so on. They all train on those images separately. And then at the end of the batch, they exchange their weight updates. Everybody learns from every image, even if they didn't see those images. And then you go do the next set of batches. So data parallelism is easy because the communication is relatively small. The training is done essentially separately on each batch. And there's this one little exchange of weight updates up at the end. But that's not enough performance to get us to the 10 to the 7th. So the next easiest thing to do is sort of the vertical dimension here is what's called pipeline parallelism. If you look at any neural network, it's a bunch of layers. If you look at transformers, there's typically a couple matrix vector multiply layers followed by the attention layers, and that's one layer of the network. Llama 70B is 80 copies of that. And so you can take each of the 80 copies and run them on a separate GPU. You can even take each of the matrix vector multiplies that are being done in those layers and run them on a separate GPU. Then all you have to pass from one GPU to the next is that set of activations that comes out of that layer's computation. So again, it's a relatively low communication overhead decomposition. The harder thing to do is going in this direction is tensor parallelism. It's where I take a single matrix multiply or matrix vector multiply and I break it across GPUs. And I do that by taking the matrix and slicing it. Think of the simple case where I have a matrix, I slice it in half, I multiply both halves by, let's do it by a vector, and now I just have to take those 2 parts and add them back together. And so there's a reduction required to do the tensor parallel. But we typically take all 3 of these dimensions and exploit them to get that last factor of a few thousand to get us up to 70,000 in that period. And to make that feasible, we've worked at NVIDIA, not just designing the GPUs with ever-increasing arithmetic performance due to complex instructions and Bruce precision data types. We've also worked very hard on the communication, starting in the Volta generation. We did our first generation NVLink and NV switch. And the latest instantiation of this in Blackwell is a single cabinet we ship with 72 Blackwell GPUs and 36 of our Grace CPUs connected entirely electrically. And the reason we do it electrically, and we think this is something that hopefully in a few years we'll overcome, is today optical signaling is about an order of magnitude more expensive per gigabit per second, about a factor of 3 more energetic, but basically 3 times the amount of energy, and also significantly less reliable. It's one of these things that tends to fail and require components in the data center to be replaced. So by packing a lot of GPUs together, 72 of them, this winds up being over 100 kilowatt rack. We can keep the connections between them short enough that they can be done entirely electrically, which reduces the cost, energy. Yeah, question?
What is the height scale?
That's a standard 19-inch rack. It's about 6, 7 feet tall, and the switches are in the middle. So the longest cable. So these are GPU boards, and all these boards in the middle are switch boards. And so the longest cable is sort of from this GPU board to that switch board, and it's under a meter. And then from there, we scale up. This is actually an older version of that rack. It's not quite as packed densely. We take these racks that are connected with NVLink, which is our scale-up network. We use it to scale a single solution running tensor or pipeline parallelism. And when we connect it with, in this case, it was an InfiniBand network. A lot of people today will do either InfiniBand or Ethernet network to connect these racks together to do the scale out. And that's typically where the data parallelism happens, or different clients running different workloads. And just as an example, within NVIDIA, we run our own data centers, both for internal use and for product use. And over roughly the same period of time, our largest system, which was actually pretty small back in the Kepler generation, has grown by 70,000x in terms of its computing performance. So not quite the growth that's been needed to train models, but just shows that everybody is building larger data centers these days. So that's the hardware side of things. If it was just hardware, I think the space would be a very different one today. The software is probably the harder part of this. One way to think about this is the computations you do in deep learning are essentially matrix multiplies. And back when I used to teach the introductory logic design class at Stanford, I think if I assigned toward the end of the quarter, design a matrix multiply unit to the class, most of the students would do a pretty good job. They come up with a pretty efficient matrix multiply unit, even if you added the I/O to connect it to DRAM and to some networking devices. So turning out the hardware is actually the easy part. At NVIDIA over the years, we started playing with deep learning in 2010. It came out of a breakfast I had with my Stanford colleague Andrew Ng, where he was working at Google at the time, finding cats on the internet. Now, why people would want to do that is another question. But I simply observed that he was using 16,000 CPUs for this computation, and then we could probably do it on a few GPUs. So I assigned a researcher at NVIDIA, a guy named Brian Catanzaro, who now runs our applied deep learning research group, to work with Andrew and port this software to GPUs. And the software that came out of that effort became cuDNN, which is one of these blocks here. So it's actually inside one of these blocks here. But we basically start with our hardware here, and we produce layers of software on top of that that build on the CUDA ecosystem to provide turnkey solutions for total end applications running from Modulus, which I think we have since renamed to Physics Nemo, which does physics simulations, things like computational fluid dynamics, hydrodynamics, E&M calculations. Clara is our healthcare software, which uses generative AI to generate proteins and molecules of various types. Running across here, Drive is our AV stack. Isaac is our robotics. Metropolis is our smart city, and so on. And so for whatever application a customer has, they can typically at least get started with software that works and works fairly efficiently right out of the gate. And I think this is actually probably one of the bigger barriers to entry in this field, is anybody can knock out a matrix multiplier. Putting the software stack behind it to make it useful and efficient is much harder. And one measure of this is the sort of independent benchmarking that's done through an organization called ML Commons that every 6 months publishes MLPerf, and they alternate between MLPerf training and MLPerf inference. And the MLPerf training results just came out in the middle of November. And NVIDIA won every MLPerf training benchmark. And it sort of shows the improvement generation to generation. So this is going from Hopper to the first generation Blackwell to the current, what some people call Blackwell Ultra, the GB300 generation. And over that period of time, it's been a 5x improvement in performance. What doesn't really show in this graph, so I thought I would show this one, which is from an older version of MLPerf. This is going from the 3.1 to the 4.0. We just did 5.1, so this is about a year and a half old. Is that on the same hardware, it gets faster over the period. So this was a 6-month period from 3.1 to 4.0, and one benchmark got 2.5 times faster, another one 2.9 times faster. And that's because getting efficiency is non-trivial on these applications. When 3.1 came out, Hopper was hot off the press. We didn't have time to tune any of the code. We just kind of ran the obvious, out-of-the-box code, and we got pretty good performance, the gray lines. But after tuning the code, things get a lot better. So that's where we are today. Let me talk about what keeps me up at night and what I think our challenges are going forward, since this is a trends talk. So one of the things is, for a while, deep learning was running a model. Whether it was an image model, you took an input, an image, you fed it through a bunch of layers, you got an answer out. That's a cat. Or if it was an LLM, you took an input, some text string, you fed it through an LLM, you got an answer out, another text string. Today, most applications are not that simple. They're agentic. So you are running the LLM, but you're running it many times by an agent that actually has a lot of retained state, it has a memory, and that can use tools. A great example of a tool is a calculator. If you want to build a AI to do calculations, you'll find that if you just take ChatGPT all by itself, it is remarkably bad at doing calculations, although it's probably better than I am just doing calculations in my head. But if you take a simple, LLM, one that may even be only 7 billion parameters, and you give it a calculator, it winds up being really good at doing calculations, just like I'm much better at doing calculations. If I have a calculator, I don't have to do them out by hand on paper. And tools could be that. It could be, like in the quantum chemistry agent, it could be running density functional theory computations to calculate the energies of things. So agents with tools are far more effective than agents just using the LLM to do things. But it means the amount of work you're doing per unit of answer to the user is going up. The other thing is that kind of drives unique demands for hardware is if you look at running an LLM, there's two unique phases. During what we call the pre-fill phase, you feed in the prompt. In this case, is apple a fruit? Most prompts are longer than that. In fact, prompts can be up to millions of characters long because very often for the prompt, it's not just the question you ask. By the way, if you type a prompt into ChatGPT, it gets fed your prompt. It also gets fed their prompt, something called the system prompt, which gives it a lot of context about don't do this and don't do that, and when you answer this, make sure not to offend the user and the like. And very often you'll also say, okay, I want you to answer this question, and here are all the financial reports for this company from the last 5 years. Use this to answer that question, and that will go into the prompt. So prompts could easily be millions of characters, millions of tokens. Tokens roughly a word. And what's great about the prefill phase is it's a very parallel computation. You get all these tokens at once, and you have to multiply them by these linear layers and then by the attention layers. But because you have all the tokens at once, there's lots of arithmetic to do for each time you read those weight matrices out. Then you get to the hard part, the decode phase. And in the decode phase, out of all of this prompt and prefill phase, you get one token, yes, right? And then you have to feed that token through the whole model. Say it's Llama 7dB, all 80 layers. And you have to read that entire model, all 70 billion parameters of it. You have to do all those multiplies. You get one more token out. So you have both a huge amount of memory bandwidth you need. You have to read all the weights of the model for every token, as well as the attention matrices. And you have a latency requirement because typically there's some user-level service objective, something like 100 milliseconds per token you'd like to get. And actually, for some things I'm about to talk about, that number gets harder. So you've got to solve this in a very small amount of time, going through all these layers to get one token out. So that drives unique demands for memory bandwidth, for latency. Then another trend that's happened, starting with DeepSeek v3 and the OpenAI 01, is what people call reasoning, chain of thought, where you don't run the LLM once. And some of the online models will actually let you see. You can ask them, show me your work. And so you'll ask, is apple a fruit? And it'll basically produce a bunch of internal thoughts. Well, apples are round and they're red and they grow on trees, and fruits are this and that and that. And then it'll feed that back into the LLM again. That'll be the first, the first output will be a string where it's kind of thinking about apples. And then it will produce another output, it'll think some more about apples. And eventually, finally, it'll tell you, yes, an apple is a fruit. And for the apple as a fruit, that's kind of a trivial thing, but for some more difficult questions, for solving some of the math Olympiad questions and the like, working through those intermediate steps is really important to get to the right answer. And another thing that people will do that takes even more tokens is they won't just produce one stream of thought. They'll say, okay, here are 3 possible output strings. And then from each of those, I'm going to produce more possible output strings. And I'll have some way of judging these by quality. And if the quality falls below some level, I won't pursue it further. But I'm still evaluating a lot of nodes before I finally get to the output string I produce to the end user. So what does this mean for a hardware designer like me? Well, it means really high token rate. So if I want to deliver 100 tokens per second to a user, which is what many people would consider interactive, I may need to have 1,000 or 2,000 or even 10,000 tokens per second coming out of my hardware to get there, because I'm not just producing a string, I'm producing a string that gets consumed and produces another string and so on before I finally produce something for the user. And agents require even higher rates because they're using their tools and doing, typically you'll have a whole network of agents. And so if every token, I have to read the entire model, let's say it's Llama 405B, and the whole KV cache, which might be on the order of 20 gigabytes per user. That number varies depending on the length of that input prompt, because a KV cache is your cached attention computation from the input string. Then that's basically at 1,000 tokens per second. That says I need a memory bandwidth of 405 terabytes per second. So Blackwell is great at 8 terabytes per second, but you need more than 50 Blackwells to basically provide that amount of memory bandwidth. And so memory winds up being very critical. You can sort of view the demand here as a memory demand and an arithmetic demand. A lot of the arithmetic demand is driven by the prefill phase, which is arithmetic intensive. But the memory demand, particularly for memory bandwidth, is driven by the decode phase. And then the other thing this drives is a latency requirement. If I want to hit that 1,000 tokens per second, that means that let's say I want to do all 480 stages here, 80 layers of 6 stages per layer. If stage would be one matrix multiplier equivalent. I've got to do each of these stages in 2 microseconds. And that includes getting the input data in there, doing the arithmetic computation, getting the output data to the next stage. And typically that involves sending messages between different compute units. And so it takes some of that 2 microseconds away to actually do the math and read the memory. I've got to have communication delays that are in the hundreds of nanoseconds. And so the communication delays become very critical here, and this is driving some of our evolution of architecture. And then the final thing that keeps me up at night is the fact that every week somebody sends me a couple papers to read where somebody has come out with a new model. One that was particularly interesting about a year ago is this DeepSeek model. DeepSeek v3 came out, and it had a bunch of it wasn't really all that earth-shattering. It's sort of in pieces. It's all incremental, but put together it was pretty impressive. It had something called mixture of experts, and so this is actually something which makes the memory problem easier. So rather than reading every parameter for every token, you would look at your token and you would say, oh, this is a token about this category, and therefore I'm not going to send it to every parameter. I'm going to send it to a subset of my parameters. So I would read some number of maybe 6 experts out of 100 experts would get that token. And this basically greatly reduces the amount of parameters I have to read for each token, and is a huge efficiency gain. And most high-end models today are a mixture of experts. The other thing it did is it collapsed the attention calculation. I won't go into a lot of the details here, from the group query attention, which was kind of the state of the art at the time, to multi-head latent attention. That greatly reduced the amount of math you had to do for the attention calculation by projecting it down to a lower dimensional space before doing the computation and then projecting it back up. And so basically, there are all sorts of these things that we haven't seen yet, that haven't been developed yet. We have to make sure our hardware is flexible enough to handle all of these. So how are we going to do that? What are some future directions? And I'm going to talk about some stuff. I naturally can't talk about some of the things that are a little closer to reality. But one thing that drives where I look for improvements is I ask, where do we spend energy today? And this pie chart is sort of a budget of where the energy goes in not a GPU, but in one of the AI accelerators we built in NVIDIA research. And what you can see is it's math limited. 47% of the energy is going to math. Basically, if you're doing a good job, that should be the case. Most of your energy should be going to that math, because that's the payload. What does the rest of the energy go to? It goes mostly to memory bandwidth. So this is, writing the accumulation collector. That's where you're putting the results. 15% in the accumulation buffer. There's input buffers and wait buffers here. And 6% is data movement, the communication. So highest priority, let's make the math better. Second highest priority, let's make the memories better. And third highest priority is let's make the communication better. And I'm going to talk about some of the things on the left-hand side in future slides. One of the ones I'm not going to talk about, but it's probably worth mentioning here, is for making the memory better, one thing we've been working on very intensely is 3D memory. So memory exists at a bunch of different levels. The memory you read most often is sitting right next to the arithmetic units, and reading it is very low energy, on the order of a few femtojoules per bit. But if you have to read HBM DRAM, you're reading HBM3 DRAM is about 5 picojoules per bit, so it's several orders of magnitude more expensive. And one way to reduce that cost, and let's just say one thing driving that cost, is I have these reticle limited chips. They're 30 millimeters on a side with the HBM DRAM there. So on average, I'm pulling one of those bits from the HBM DRAM and I'm dragging it across 20 or 30 millimeters of linear communication to get it to where it's going. And that's a huge amount of energy. One thing we see as a long-term direction is to put the DRAM directly on top of the GPU and localize the computations. Now we can read the DRAM directly vertically down, and through a bunch of things that we think can go along with that, reduce that HBM memory read from maybe 5 picojoules per bit to maybe 0.5 picojoule per bit, and at the same time drive the memory bandwidth way up. Let me talk about some of these other things in a little bit more detail. Yeah?
Won't this look a lot different if you were looking at latency, the pie chart of latency versus?
Yes, it would look very different.
Yeah. And
But I'm looking at power.
doesn't that worry you just as much?
It does, but I didn't have that pie chart. That's a good idea. I'll put that in my next talk. See where all the latency goes. That's a really good idea. So let's talk about number representation. And so, a lot of us, don't really think that hard about numbers, right? We, let our computer worry about how we map bits onto the real number line. But it turns out it's a really essential task if you want to do efficient deep learning. And there are a bunch of ways of representing numbers. So integer, we have, mantissa bits. We just raised 2, each bit position raised by the power 2, and we add it up. For floating point, we do the same thing for the mantissa, but then we multiply it all by 2 to the exponent, so we get the scaling factor that can move us up and down the number line. One of the most efficient natural representations is the log representation. I'll go into that more in a while. If you're, especially at low bit precisions, if you want to make every symbol count, what you want to do is use a code book. So I want to take, say, 8 bits of symbols, look up in a table of 256 numbers. Now I can basically take each of those 256 numbers and put them on the number line where they will do the most good. Some people like to try to mimic how biological systems work, and they use a spiking representation. It turns out that in CMOS, this is almost the worst thing you can do, because CMOS dissipates power when you toggle a signal. And say I want to represent a number between 0 and 256. The average number would be 128. So it would take 128 toggles to represent that. With an 8-bit integer, on average, 4 of the bits will change state, which is equivalent to 2 toggles. So it's 64 times as much energy to represent that in a spiking representation as an integer. We've played along with analog. I get very excited about analog because the individual operations in analog are essentially free, right? If you have a voltage and a conductance, multiply just happens, right? And it turns into a current. And the problem with analog is that while the operations are really cheap, there's no really good analog storage, and it's actually very difficult to move with any precision an analog value from one place to another. So you wind up having to convert it to digital, and as soon as you do that, it turns out you lose. It actually is far less efficient than doing things digitally. So how are we going to compare these number representations? So really 2 questions. What does it cost? And here there's operation energy and movement energy. What does it take to do a multiply accumulate? That's the operation energy. And what does it take to read it from the memory and get it to the multiply accumulate? Well, that movement energy is just the number of bits, right? The bit, you're moving it. If you're reading it from memory, you're moving it across a wire. The memory and the wire don't care what those bits mean. They're just moving bits. On the operation energy, it really matters a lot what the bits are. So let's compare some of these things. So here's a comparison of spike, which I already kind of explained why it has really bad energy, but this is actually sort of showing it equivalent to integer representation power. The log representation, the floating point representation, and the integer representation. What you see is both log and floating point have really good dynamic range. Integer not so much because it's spreading its things uniformly across the number line. And what really matters for the accuracy here, this is, accuracy is described by error. And because this is reducing on a log scale, further to the right is better. For a given number of bits, log has the best accuracy and then floating point, and integer is actually pretty bad. Now, the best you can do is symbols. This is a figure from a paper that Song Han and I wrote at ICLR. It actually was the best paper at ICLR in 2015, where we talked about sort of compressing the weights into a symbol table. And what was great about training neural networks is you train them with backpropagation. And once you've computed partial derivatives, you can train anything, including your symbol table. So we actually just initialize the symbol tables randomly and then backpropagate it into them and fine-tune the weights. It turns out that you actually had to play some games to avoid having everything clustered together. But as long as you did sort of appropriate clustering algorithm, you wound up getting near optimal symbol representations. And this was a network where we also were doing pruning. So we were eliminating the weights that were near 0. So anything near 0, we clipped to 0 and took away. So the distribution of weights wound up looking kind of bimodal, right, as opposed to just being a Gaussian. And so if you're trying to come up with a representation say with 16 symbols to represent this. If you used integer, which is shown here by the x's, you'd be wasting a lot of your symbols, because it's evenly spaced representation on the number line. You're wasting a lot of your symbols out here where nothing is happening. And you only actually have, maybe 1, 2, 3, 4, 7 of your symbols where there's any density in the distribution you're trying to measure. Training this representation with the same number of symbols, which is the red dots, you're basically sampling the important part of that curve much better. And even with, this is the network that's not pruned. I forget which layer of which network this is. It's kind of a Gaussian curve centered on 0. If you want to represent the whole thing, you're going to be wasting a lot of your representation out here in the tails. And I'll talk a little bit more about that later. But let's talk about the log representation, since it's one of my favorites. Those of us who are old enough when we started doing computations used things that looked like this. It's a slide rule. And what it's really doing is it's doing a multiplication by converting it to logarithms and then sort of in space doing an addition. And that's the real power of the log representation is it turns multiplies into adds. We're not going to talk yet about what it turns adds into. It's great. So if you compare the dynamic range and worst case accuracy to int8 and FP8, it has much better dynamic range and accuracy than int8. It's got comparable dynamic range to FP8 and about 30% better accuracy. And I always find it's good to view this graphically. So the reason that the log number system is a great representation is the error is proportional to the value. So on the left is log, and this is basically a 4-bit log representation. And so when the numbers are small, the quantization error, which is sort of the size of these steps, half the size of these steps, is small. So it's 9% across this entire range. Whereas with integers, the size of the error is the same everywhere. So it's enormous, right? When you're trying to represent 1.5, your error is a half, it's 33%. And then it gets smaller proportionally because the absolute value of the error is the same, whereas the number you're comparing it to is getting bigger. Now, log is a great representation. One of the reasons it hasn't caught on that well is because floating point is almost as good. So log is on the left here, and again, the error, the quantization error, the size of these steps, is exactly proportional to the number. With floating point, it's sort of like halfway between the two. You start out with a small error, and you keep that for a couple jiggles, and then you make the error twice as big, and you keep that for a couple jiggles, and so on. Each time you step the exponent one. And so, again, you wind up with the same dynamic range, but with a little bit bigger error, but not nearly as bad as integer. Now, what has kept people from really embracing logs is the adds. So you want to add multiply two log numbers together. It's easy. You just add them, right? Because that's a multiply. You're adding the exponents. If you want to add, what you have to do is you have to convert it to integer, which requires a table lookup, do the add, and then convert back. Now, you can think of our log representation as having an integer part and a fractional part. So these 4 bits is just 2 to that value, right? So you're just doing a shift. But these 3 bits, you're doing a lookup, because you have to look up what is 2 to the 1/8, 2 to the 1/4, 2 to the 3/8, and so on for each value of those 3 bits. And that's expensive. It would be very expensive if you had to do it for every add. But think about what you're doing in a typical deep learning accelerator. You're doing a matrix multiplier or a matrix vector multiplier. You're doing a bunch of long dot products. Long meaning very often 1,000 or 10,000 elements. And so what you can do is say, okay, I'm going to add 10,000 things. I'm going to sort them so that those that have a fractional part of 0, I'm going to sum them all here. And say, I'm basically binning it into 8 things. So if I had 1,000 things, I'd have 125 of each of these on average. They wouldn't necessarily be equal. They don't have to be equal. But I basically partial sum these, and then I do a single lookup of 2 to the 0, 2 to the 1/8, so on up to 2 to the 7/8. Do that multiply, and then sum the 8 groups together at the end. So this is from the US patent on how to do efficient deep learning with log numbers. And so you can basically make the adds palatable by postponing the bad part of the add and doing it once for 100 or 1,000 numbers instead of for every add. What happened there? That's not good. Hello. Okay, there we go. I must have touched something. Okay. So the next thing that's really important to, in our journey to better number representations is to understand what numbers to represent and what numbers to throw away. And so whatever number representation you pick, if it's integer, if it's log, if it's floating point, pick the range optimally. And what do I mean by that? So what we did when we started out building these machines for deep learning is we decided we have to represent every weight, right? So if I have some weights that are way out here at minus 0.8 and 0.8, I would take my 16 numbers that I can represent and spread them on the number line like this, which gives me a really large amount of quantization noise and absolutely no what I'll call clipping noise, which is the noise introduced by throwing numbers away. It turns out that if what you want to do is minimize your error, you're much better off representing like this, where my quantization noise gets really small. And yeah, I'm throwing some numbers away. I'm not throwing them, I'm clipping them down to the highest representable number. But there aren't very many of those. So the amount of noise I'm introducing by this is small. And in fact, you can pose this as an optimization problem, where what you want to do is minimize the mean squared error of the representation for a given number of bits. And if you do, you wind up with this integral, which is hard to evaluate. But also you wind up with this iterative representation of it, which is easy to evaluate and can be done in hardware very quickly, which is important because for the weights, you can do this offline before you start the inference process. But for the activations, every time you produce these activations, you have to decide what the scale factor is and how to clip them. So you have to do that iteration and get there. But the great thing about this is it winds up being worth almost 2 bits. So let's look at one of these lower ones, because I can point out that those are too high. Let's say I start out with a 4-bit representation, and I'm basically not going to clip. So the clipping scalar here is the largest number I can represent. So here I have a lot of quantization noise, no clipping noise. As I move to the left, I'm saying, OK, everything above 3, I'm going to clip to 3. Everything above 2, I can clip to 2. I'm reducing the quantization noise by more than I'm introducing clipping noise. Until you get to the minimum, that's when the quantization noise and the clipping noise are the same. That's where I stop. That's this optimal point that these do. And then if I go over here, I see that I'm getting with 4 bits almost the same mean squared error that I was getting with 6 if I didn't do this. So this is one of the things that's allowed us to scale down our number of bits without really losing precision. Yeah?
Error sounds like a really good heuristic, but given how magical stochastic gradient descent is it actually optimal? Do we have reason to believe?
That is a really good question. And my answer is I don't know, but it would be interesting to try to test that in some way by putting yourself at the minimum error point, seeing what accuracy you get on the actual benchmark, and then dithering one way or the other and seeing if the accuracy improves or not. It's much easier to minimize error than it is to actually do the computation required to actually compute the accuracy. But it'd be interesting to try that. It's a good idea. The next thing we realized is that this whole issue of scaling and clipping can be done at different granularities. And at the time we started this, we were doing it at the granularity of a layer. So an entire layer of a neural network, we would pick one scale factor and clip everything optimally to minimize the mean squared error for that scale factor. But then we asked the question, this is a paper we had in MLSys in 2021, what if we did this at a smaller scale factor? So for example, if every 64 elements of the matrix we took and we scaled, now instead of having to take a huge distribution and scaling it, we can take a smaller distribution and scale it. And this wound up sort of buying us another bit. And actually in the representation called NVFP4 in Hopper is FP4 grouped into vectors of 16 with an FP8 scale factor. And then something I've been working on for a long time is sparsity. So Song Han and I wrote this paper at NeurIPS in 2015. We showed that you could take a typical neural network of the day, and for an MLP, a multi-layer perceptron, lop 90% of the weights out of it and lose no accuracy. And it was kind of an interesting result, and we had real trouble converting that to actionable advantage in hardware. And the reason is, when you're doing a dense matrix multiplier, it's a super nice regular operation. The numbers kind of march by each other, and you do the multiplies, and you do the adds, and answers fall out, and it's all very regular. Once you start introducing sparsity, it becomes very irregular, and that irregularity introduces a lot of control. The thing that finally wound up working after many failed attempts was structured sparsity, which we introduced in our Ampere generation. And the idea here is we'll take a dense trained matrix, will basically take the low values, force them to 0, with the constraint that out of every 4 elements, at most 2 can be non-zero. We can take this and squeeze it down so all the non-zero elements go away, add some metadata to it to say which ones they were. Now we take this metadata and we basically use it as the select input to the multiplexer that's feeding the activations in, so that we feed the activations that correspond to the non-zero weights in, and it becomes a very regular computation. You know, you're not doing any control here. You're simply doing a select on a multiplexer based on that metadata. So this works out very well, but I think there's still a lot of gain left on the table here, because we're doing only 2-to-1 and we're doing it only for weights. I think one of the areas we have to mine a lot better performance in the future is doing sparsity on activations as well, and doing more aggressive sparsity than just 2-to-1. So let me move on to the next step here, because I see my timer counting down here. Let me talk a little bit about accelerators. One way we kind of prototype ideas for how to make deep learning better on GPUs is we take the ideas and we put them in accelerators first. And we built a number of these over the years. These are some chips we've done in NVIDIA research. And accelerators get their gains by a bunch of advantages. The single biggest advantage that accelerators get, we've kind of already taken care of with GPUs, and that's this notion of instruction overhead. Remember, I said early on that we had this 20x overhead for GPUs doing a single floating multiply add. This is a figure I pulled from a talk which talks about it on CPUs, which are way worse than GPUs. So here, if you're doing a 16-bit integer add, which is a 32 femtojoule operation I think this is in 28 nanometers, so I normalized it to this paper that did this all for the ARM architecture. And you compare that to what it takes to do the add instruction on an ARM A15, which is relatively tame out-of-order processor. This overhead would be even larger on a modern ARM Neoverse or on an AMD or Intel processor. It's 4 nines of overhead. So it's basically you're doing 10,000 times as much energy in the overhead as it is in the operation. So it's only 20x on GPUs, and with the matrix multiply instructions, it's a few percent. Limiting instruction overhead is probably one of the biggest things we get out of building accelerators. The other is we can kind of pick operations tailored to minimize energy. And again, this sort of shows what I said earlier, that the arithmetic, and this is actually from a paper that Mark Horowitz had at ISSCC a number of years ago, that the cost of doing arithmetic goes linear with bits for add, but quadratic with bits for multiply. But what I didn't say when I did that is that reading a memory costs more than any of that. And going across wires is even more expensive. So one of my basic principles is every time you sort of go out of a realm of locality, it's an order of magnitude more expensive. So if I'm reading from a local SRAM, that's like 5 picojoules per word. If I read from an SRAM somewhere else on the chip, that's 50 picojoules per word. Now, don't think of that as memory energy. That's communication energy, right? It's the same SRAM, right? I build my SRAMs with small macros that might be 8 kilobytes apiece. And so if I'm building an on-chip SRAM that's megabytes, that's a whole bunch of these little 8 kilobyte SRAMs that cost 5 picojoules per word to read, and then it's 45 picojoules per word to get it to where I need it to be. And then if I have to go off-chip, it's another order of magnitude to read DRAM off-chip. Yeah?
Doesn't architectural balance also bother you? Like if you're doing a decode-only transformer accelerator, you basically want a giant HBM machine, whereas you have to proportionally allocate HBM, these MAC arrays.
Yeah. No, the problem, and it's actually not cool. You want a big HBM machine. You may actually want a big machine which is a bunch of SRAM with math units sitting right at the edge of the SRAM. But yeah, right. Well, it's a question of if it fits, and how many chips does it take to fit. But the problem is if you provision for one phase, like if you provision for the decode phase, you'll wind up being very RAM heavy and math light. And then during the prefill phase, where you actually want a lot more math because you're doing many tokens at once with the same weights, you would provision way more math and less RAM. And so you can't balance simultaneously for all parts of the workload. And that's why we recently announced a CPX part, which is basically a prefill optimized GPU. And you can imagine that you can build decode optimized GPUs so that you may have to specialize the engine for different things exactly to achieve that balance.
And you feel like an accelerator wouldn't have advantage here because you need 2 accelerators
It's exactly the same as the GPU. I can balance the GPU and you can balance the accelerator. It's how much math and how much memory you provision. And how much bandwidth. Those are the three variables. How much communication bandwidth, yeah. I'm running out of time, so I'm going to skip over this kind of slightly. One of our more successful accelerators is Magnet. This is the diagram of it. I'm not going to go into a lot of detail there. But we basically use these to see what is the speed of light in terms of ops per watt. And what you can see is doing some aggressive voltage scaling here. We're at about 100 teraops per watt doing deep learning inference on this particular accelerator. And we use that then as a bar to say, can we get our GPUs to achieve that by taking the techniques we implemented in Magnet, many of which found their way into Blackwell to do that. I should say that this voltage scaling is a huge opportunity if your goal is to optimize performance per watt. And there's this conflicting set of goals that you want to optimize performance per watt. You also want to optimize performance per square millimeter. And if I want to optimize performance per watt, I should not have stopped at 0.5 or whatever it was there. I should have scaled it, I should have set really low threshold voltage and scaled down to like 0.25 volts because I'm winning quadratically as I scale that voltage. But I'm also increasing the area I require to get a certain arithmetic performance linearly. So I'm getting more back on energy efficiency than I'm paying on square millimeters, but I am making my performance per square millimeter worse. And there's some very clever techniques with this thing called voltage stacking, or because it's very hard to regulate, say down to 0.25 volts. What I would do is I would say, okay, I'm going to regulate to 1 volt, and then I'm going to take my matrix multipliers and I'm going to divide them into 4 units and stack them on top of each other so that the ground of one unit becomes the power supply of the next unit. So, but then I have to make sure they dissipate exactly the same amount of current to keep everything balanced. But it can be done, and we've done some prototyping of that. So let me move on. One of my visions of accelerators in general, so I build accelerators not just for deep learning, but for bioinformatics and for SAT solving and some other things, is that it turns out 90% of the problem if you're building one of these is the same every time. You have to build a memory system with both, off-chip memory, HBM or GDDR, LPDR, and on-chip memory. You've got to build communications off to the off-chip memory and on-chip network on chip, communications off to the rest of the machine. And you need some general purpose computing. And then for whatever your application is, there's a tiny little piece you do. It turns out when one of my PhD students and I built a bioinformatics accelerator, the part of it that was the core of the dynamic programming for the Smith-Waterman algorithm was like 1 page of Verilog out of many hundreds of pages. So what you'd like to do is have a system, it's like a GPU, that has all these common elements, the general purpose compute, the memory system, the interconnect, and then have a programming system where you can say, here's my application, and the mapper decides how to take that application and map it in space and time, how much of that mapping goes to general purpose compute blocks, the streaming multiprocessors of the GPU, and how many synthesize to custom compute blocks. And with your modern chiplet technology where we can stack those, you can imagine having one base layer GPU that can be specialized for many different applications by stacking those on top. That's just kind of a vision I have. It is not a vision the company has. So let me wrap up here, and then maybe there's some time for questions. I think I'm over the hour already. So I think deep learning really is improving the human experience, and we're only at the beginning of that. I think most of the real gain that's going to happen in the next few years is taking the models of the quality we already have and applying them more effectively to improving productivity in various human endeavors and just using them better. But at the same time, we are going to build better models. I think a lot of the current challenges we're facing, this disaggregated inference where the pre-fill phase is math heavy and the decode phase is memory heavy and completely latency limited, is causing us to think hard about how to do our architecture. And what's driving the latency problem even harder is this notion that we're going to do chain of thought and tree of thought. We're not going to run the LLM once. We're going to run it tens of times for every response to the user. And people are coming up with new models every day, particularly new attention mechanisms. I think that's where I see most of the creativity coming. And part of it is that right now when you do attention, it's quadratic, right? I have to have every token I produce attend to every token in the whole input prompt and everyone I've produced since I began responding. And if you think about it, that doesn't make sense, right? Most words don't depend on every other word. They depend on certain keywords. And so there's a huge research area in basically pruning the attention, coming up with sparse attention, so you can get a scale factor for that attention that's less than quadratic. Deep learning was enabled by hardware. We had the algorithms, we had the data. It wasn't until GPUs came along that we basically allowed those two to be combined. And since then, we've been scaling at this breakneck rate, 16x per year in the transformer era, 10 to the 7th in a 12-year period. And to keep up with that demand, we have scaled the inference performance of our GPUs by 1,000x in the last 10 years, 5,000x in 12 years. And 3x of that was from process technology. The rest of that was number representation, complex instructions, and sparsity. To get the rest of the 10 to the 7th, we have done scale up and scale out. You now need 10,000 to 100,000 GPUs to train a large model. And it's not just hardware. Again, matrix multipliers are easy to build. To get usability and performance requires very optimized software. And I've given some details about some of the optimizations we've done in number representation by doing an optimal trade-off of clipping noise to quantization noise. Basically doing that scaling on a relatively short vector. We wound up with 16 elements in Blackwell after doing a bunch of studies. And then exploiting sparsity in a way that can be made regularized so you don't pay for that irregularity. So with that, I'll show you a picture of where I live, and I'd be happy to take questions.
We got a mic. We're going to run those.
Sure. So thank you for the great talk. My name is Desvon. I'm a PhD student here. So my question was, it wasn't really the focus of this talk, but I'm curious about your thoughts on interconnect technology, especially NVQLink. I asked this because I was at the supercomputing conference last 2 weeks ago when Jensen came and gave a talk about this key technology being a factor of the future scaling. So what was discussed was latency and memory bandwidth and making sure that that is important for deep training inference and doing your model training. So how do you, from your perspective, how do you think this will shape future hardware? And
yeah, well, interconnect's critically important. I mean, there's sort of three ingredients to building any engine for AI. There's math, there's memory, and there's interconnect. And the interconnect's important both to provide enough bandwidth to take the problem and distribute it geographically, whether it's on chip or across multiple chips. But it's also a big driver of latency. And one of the things we're trying to do is to get closer to what's possible. Right now, if you look at our latencies going through NV switch and NV link, it's order of, many hundreds of nanoseconds per hop. And what's possible is, maybe 100. And so there's big opportunity to go further. Now, you mentioned NVQLink. That's a technology that we're providing for people doing quantum computing. And it's a step, but what's actually really, it isn't really quantum, right? It connects quantum boxes together, but it doesn't do it in an entangled way. What's really needed for quantum computing to scale is a way of having qubits in two different boxes that wind up being entangled, so the fate of one is determined by the fate of another. And that's something that we don't know how to do yet, nor has anybody else really tackled. Yeah.
So I heard you assign a lot of the energy to the math operations, and that's very frequently done. But if you look at it very closely, the actual mathematical operation should take very little energy. And the problem is you've got to bring the data in, got to get the answer out. So if you look at it more closely, actually it's also communications. And that maybe over 90% of the energy should go into communications.
Yeah, well, actually, for the pie chart I gave you, that was from the magnet chip. And we actually were cutting the math operation energy at the input of the math unit. So we'd already accounted for the communication energy separately. And that's an accelerator that was very carefully optimized so that most of the numbers being presented to the math units were coming from very small memories sitting right at the inputs of the math units. And so, but in the general case, you're right. In the general case, a lot of the energy is moving to that.
I think even if you go, if you reference right at the at this plane, you still have to go to the exact device.
That's right. Yeah. So I was counting the wire from the boundary of the multiplier to the AND gate as for the multiplier. But we could argue about who that should be accounted to.
Yeah.
Appreciate it. Love the talk. My name is Matei. I'm a grad student here working in robotics. So the data seems to support that the limiting factors thus far has been hardware. So we've had the data and I guess the algorithms since 2018. But we're getting to a point where one of these NV72 racks takes about 6,000 times the power of the human brain. So I'm wondering if you see these trends continuing to hold, or if at some point you think we might, be looking in the wrong direction.
That's a really great question. First of all, let me clarify. I don't think the limiting factor right now is hardware. So hardware was a limiting factor to get the deep learning revolution started, and it's certainly one of the limiting factors. But when I both talk to our people who build large models and I talk to some of our customers who build large models, they are probably more limited by data than they are by hardware at this point, that they don't have enough training data to get their model to the next step. There was a time when buying more hardware was doing it because you could continue to mine the internet, for data that was essentially free just by having some crawler go over the internet and suck data down. All the easy data has been sucked out at this point. Now people are finding it much harder, to get data, which is why there's a trend moving from scaling performance of models from just building bigger models, training on more data, to doing what's called test time training, where you try to get the model to make itself smarter by iterating on the problem. So that's sort of the first half of your question. The second half is, yeah, so the human brain is, probably around 20 watts and does an amazing job of a lot of things. And, one of our racks is, over 100 kilowatts. So, and can't do certain things that a human brain can do. So, to me, that's a huge challenge to figure out how the human brain works, which I don't think we really have much of an idea. I don't think it's so much whether it's analog or digital, it's how it's organized. And it's organized in an extremely efficient way that's been honed by, hundreds of thousands of years of evolution, both of the human brain and simpler mammalian brains that preceded it. Yeah.
Thanks, Bill. A really great and inspiring talk. You mentioned voltage stacking towards the end there, and it's something that we worked on quite a bit, and it would be a really elegant solution to a power delivery problem that would scale really well. One challenge of that is that your logic sits in different voltage domains, which tends to be difficult in advanced CMOS processes if it's a joint substrate.
Yeah, no, it requires level shifters between those domains, and the level shifters have to have transistors that can tolerate, the extremes of that domain. But if you can basically package a large enough module into each of those domains, you can amortize the cost of those level shifters.
And do you think that are you guys big enough to convince the process manufacturers to embrace things like SOIs and other things that you might be needed for that?
Well, yeah,
or would you be okay with taking an older process because you save enough energy by doing that?
I don't think we're going to move back to an older process. And we certainly are large enough. We have the attention of the manufacturers. Whether they will do something or not is another question. But what we're looking at right now would actually, we're talking about basically stacking 4.25 volt domains, which will actually work perfectly well in a bulk CMOS process.
Great, thanks.
So do we have other questions?
I have a slightly mad question. So I'm wondering, in 10 years, if I had to ask you, what's your projection going to be? How many thousand times or how many million times is it going to be? Like, how far do you think we'll go?
Oh, so what the performance
in terms of
will be in
compute?
10 years? That's a really good question. So nobody will remember. I found that you can predict whatever you want because nobody remembers your predictions when they're wrong. And they say what a genius you are when you're right. So if we continued scaling at our current rate, we continue doubling every year, and it would be roughly another factor of 1,000. I personally don't think we'll achieve that. And the reason is, our scaling so far has been doing things like reducing the precision of numbers, and that's mined out. We're down to 4 bits. Maybe we'll get to 3. Maybe 4 is the point of diminishing returns. I think there's some more we'll get out of sparsity. I think there's some more we'll get out of more efficient machine organization. And if you think on a logarithmic scale and say maybe we'll get half in the next 10 years what we got in this 10 years, then it'll be like a factor of 30. So I'd be very disappointed if we didn't get 30. I'd be very surprised if we get 1,000. So it's between those two numbers.
Very wide range there. All right, one more question.
Thank you for the great talk. So you explained how bad spiking was in CMOS, and but spiking is how our brain works. So do you think there is a paradigm beyond CMOS that could?
Yeah, no, we're always looking at new logic technologies and other ways of doing things. And it's possible that if you had a completely different technology, it would make sense. I mean, when people first started building airplanes, they looked at how birds worked. And so they built things that flapped wings and had feathers. And it turns out that if you're building aircraft with the technologies that are available, be it wooden, fabric, or aluminum, that's not the right way to build them, right? So what you have to do is you have to look at the implementation technology you have and ask what is the right representation in that technology.
Thank you.
All right, we've got another one in the back here.
Hi, thank you so much for the talk. You mentioned in the beginning, you're talking about like the sizes of the transistors, and if I'm not mistaken, I think NVIDIA uses a 4 nanometer process. Apple uses 3 nanometers, and the sizes are getting smaller and smaller. But at a point, they can't make them much smaller than a certain size because you get closer to the size of the atoms. What do you think is going to happen then in terms of improving performance of GPUs? And
well, I mean, we've already gone from an era where we were getting a lot out of process technology. Back up till about 2005, we were in this era where people did what's called Dennard scaling, where every time we would reduce the line width of the process, we'd also reduce the supply voltage, and that way we wound up winning sort of cubically as we reduce things, because we would get a linear reduction in capacitance. Two of the dimensions were reducing, another one was going the way that increased capacitance. But we were also getting quadratic gains from the supply voltage. So we were winning sort of with V cubed scaling of energy, or I should say linear dimension cube scaling of energy. Since that point, we've been getting very marginal returns from process technology. And you should also take the 4 nanometer number with a half a pound of salt, because there is some dimension which is ostensibly 4 nanometers, but to me the dimension that really matters is what the metal pitch is, and the metal pitch has not changed very much in the last several process generations because it's lithography limited, and even with the jump to EUV lithography, it's still something like 30 nanometers, a really good measure of a process technology which takes that metal pitch into account is to ask, what is the SRAM density in that process technology? And the SRAM density has been largely unchanged since the 7 nanometer generation.
Thank you.
I didn't answer your question, though.
All right, any last questions here for Bill? No, last call. All right, I think that's a wrap. Thanks so much, Bill, for joining us.